We are now on to a discussion of some of the key processes that cause landforms to be shaped geomorphologically. And we're going to start off with river systems and streams. We're going to start, though, talking about the idea of a drainage basin, which is pretty fundamental for understanding how streams work. All streams have a geographic area from which they collect water. That geographic drainage basin, or watershed as it's sometimes called, is bounded by drainage divides, which are the high points between one or more watersheds. The map that you see on the right here shows a couple of watersheds in the Turnagain Arm area. On the right, we see Bird Creek and Penguin Creek. On the left, we see Indian Creek. Any water that falls within one of these drainage basins ultimately works its way down towards the creek if it's not evaporated away. The lines are the height of land or drainage divides, and you can see here the very well-known Bird Ridge, which divides the drainage basin between Indian Creek on the west side and Bird Creek on the east side. In addition to creeks having watersheds and drainage divides, they also have drainage patterns, and those patterns can tell us a lot about what's happening underneath on the ground as the water flows, either geologically or in terms of its slope, or what might have happened relatively recently in geological history, like the ice ages that often produce deranged drainages like this. If you decide to complete physical geography assignment number 6A, you will be required to do a little bit of research on drainage patterns, take a look at the text that shows these different drainage patterns and talks a little bit about how each of them are created. Make sure that you don't just look at the very finest streams in a drainage area. Those often look quite dendritic. When you zoom out a little bit and take a look at the bigger picture, you often see these more interesting patterns here. A stream can be said to have a gradient and to discharge its water at its base level. What does that mean? Well, the gradient, number one, refers to how steep a stream is. Streams generally, at their origins, are relatively steep compared to what they are at their base level as they've moved their way down through a watershed. That's because they're still doing eroding up in the high part of the watershed. As they move lower and lower down, they often start to deposit more material, and there you start to have a much lower, less steep grade. Now, of course, this varies a lot depending on where you are. Looking at a relatively young mountainous area like Alaska and comparing it to Florida, there's no real good comparison there. The base level is where the stream ultimately discharges its water. That could be into another stream, it could be into a lake, it could be into the ocean, or in very rare situations, it might just be onto bare ground. The stream discharge refers to the amount of water that is discharged by a stream or a creek, usually every second or every minute or every hour. Now, as we can imagine, generally stream discharge increases over distance. So the longer the stream has been flowing and the more water that's been feeding into it, the more water there will be in the stream. There are some rare exceptions to this, particularly in desert areas where we have something called exotic streams that evaporate as they flow. Stream velocity also changes as well. Generally, streams are much faster when they're up in the less graded area of the watershed, and then as they get down in the lowlands, they begin to be slower, though there is more volume, which often means that they can do more erosion. The turbulence of a stream generally decreases as well as a stream becomes more graded. As a stream discharges, it's very strongly influenced by what's happening in terms of local weather and climate patterns. It has a base flow, which is sort of the average expected flow from an area, but there are definitely peaks of flow when we have a big rain event or as snow starts to melt off in the spring in a northern location. This is because water is flowing directly over the land into the watershed, or it's moving down through the soil, and that can be increased during big rain events. Every stream's a little bit different. Every stream acts differently based on how dry it is, how much vegetation there is, how steep it is. This is a Google Earth map that shows parts of the Yukon River, which you can see sort of flowing through here from the Yukon all the way down through Alaska. This is a relatively small tributary of the Yukon called Wade Creek. And what you can see about Wade Creek is that its discharge very rapidly increases after there are big rain events, and then it slowly discharges over time. The amount of discharge in cubic feet per second here is only somewhere around, at its peak, 2.47 feet. As Wade Creek feeds into the larger Yukon River, the pattern changes considerably. We can no longer see these individual rain events as clearly, though we can see increases, in this case, sometime during the end of July, when we hit a rainier phase in this area. Here on the Yukon River, the discharge has increased to 151,000 feet per cubic second. The Yukon River collects water from a lot of different tributaries that feed into it, and by the time it gets to Galena, it is twice the size that it was back in Eagle, 342,000 cubic feet per second. And we see now an even smoother profile of water flow through the watershed, though it does appear very rainy events all throughout this part of Alaska at the end of August caused increases to occur. So discharge fluctuates a great deal depending on what's happening in a watershed, but also how big or small that watershed is, or how steep that watershed is. Now, once the water gets into the stream itself, it moves through a channel. And as it moves through that channel, it erodes and it deposits material. What's causing that erosion? Well, part of it is just the hydraulic action that's taking place within the creek. But the creek also causes material to be bounced along. It causes large boulders to tumble along the bottom, especially if it's a very powerful creek or river, and it causes abrasion in the channel itself. Material is carried in the stream either as suspended and dissolved load, or as material that is dragged along the bottom through traction and the bouncing of particles called saltation. A creek's ability to erode material and move material is often referred to its competence. A very competent river stream can move really big stuff. The capacity is often based on what the discharge is, but the discharge can also, to some extent impact the competence of the stream or creek as well. There's a great deal to understanding exactly what's happening within the dynamics of the stream itself. Obviously, when a stream floods, it scours out its channel, it has a greater competence and capacity and carries a lot more material with it. Streams that are in a channel do some other pretty interesting things, especially the streams that are in what are called single threads or largely in single threaded channels. These streams tend to, when they become quite graded, meander a great deal, which means they go back and forth across the landscape. And as they do that, meandering, they cut into bank areas and they deposit small little bars as well. They get to the point where eventually the meanders become so large that they begin to cut off their own meanders, creating what are called meander scars and oxbow lakes. The best way to understand this is actually to take a look at some pictures of this. So here is a map of the East Mount Carmel area of Indiana, of all places. And you can see the White River is meandering in its single channel a great deal throughout here. It's created, though, old meander cutoffs in the form of oxbow lakes here. There are also meander scars, like the cypress swamp area right through here. And this long pond is almost another stream channel itself that's been cut off through meanders. So this is very commonly seen in streams and rivers all over the world where, number one, there isn't a huge amount of material to move, and also you have a relatively graded situation. Now, when you do have large amounts of material, you can have stream channels that are called multiple thread or braided channels. And braided channels tend to be very complex. Some great examples of them occur all around Alaska. And the McKinley River is a great example of one. You can see many channels that move through this area. And this is because it's being fed by the Muldrow Glacier back here. When spring is at its peak and there's a lot of meltwater from snow and ice, the McKinley River picks up huge amounts of material that are then taken down through this relatively graded area. You can see not a lot of contour lines here. And as it loses its competence over time, as spring ends and the melting stops, that material just gets deposited all over the place, blocking its own channels and created these threaded or braided channels. Very typical in Alaska. The last thing I want to say about meandering and about channeling is that oftentimes we get some interesting single-threaded channels that have interesting meanders in them. And then an area is tectonically uplifted. And when that happens, meanders often become entrenched in the local geology. So let's take a look at an example of that in the Grand Canyon, where we see the Colorado River in a large meander right here has been entrenched, and that meander from a previously more graded river has essentially been preserved in the landscape. Here are a couple of images that show some of this meandering and the formation of an oxbow lake. And then this is a satellite image that shows the upper part of the Teklenika River, where you can really see all the many braided channels looking down directly at this area. Once streams have become quite graded, they'll start to deposit material. They deposit that material in relatively flat areas that are called floodplains. Some of the biggest floodplains in the United States include the floodplains of the Mississippi River, and we're going to take a look at a map of that area in just a little bit. You will often find many of these meander scars in an area like this, but you find some other pretty interesting features as well, including what are called natural levees and back swamps, which themselves help produce a type of river or stream called a Yazoo stream that runs parallel to the main river. So let's go take a quick look at a map that shows this. This is Thibodaux, Louisiana that we're looking at right here. And Thibodaux is a relatively small city in the middle of Louisiana, not far from the Mississippi River. There is a small river, though, that flows through it. It's a distributary of the Mississippi. So the Mississippi, as it becomes a large delta area in the very southern part of the United States and Louisiana, lots of little rivers come off of it and distribute its water to the sea. And the Bayou La Fourche is one of those. You'll have to take a closer look at the Bayou La Fourche than what I can show you right here on the PowerPoint. But I will tell you that if you take a look at the elevations that are right along the Bayou La Fourche, and then compare those to the elevations that you find out here, what you'll find is something very curious. The elevations are much higher near the river, and further away from the river, you get lower elevations. And that's because what we're having here is the creation of natural levees. When the Bayou La Fourche, the Mississippi River, or any of these very graded rivers floods, they're carrying a lot of material, and they flood fairly regularly in wet, graded areas like this. They drop the larger material as the stream loses its competence as it pours out of its bank. And so the larger material gets deposited right by the river itself. And then the finer, more clay material gets deposited further away. It's very fine material. And so it doesn't have as much volume to it either. We end up getting sort of nice, more gravelly and sandy areas close to the river. And then we have clay, swampy, and lower elevation areas away from the river. This creates back swamps, and you can sort of see some swampy areas here and here. And then the natural levees are along the Bayou Lafourche, and that's why many cities and towns are built right by rivers in areas that flood, which is a little bit counterintuitive, but makes a lot of sense if you understand what a natural levee is. Many of the Yazoo streams and rivers find themselves flowing in these back swamps, unable to join the larger river because the larger river has those natural levees. And that's particularly the case for really large rivers like the Mississippi River. Here's a couple of images that show some of these features again, more oxbows and cutoffs here. This is a fairly famous map of the Mississippi River that shows over here a satellite image of the river, but over here it shows all the different channels in different years. So here's a channel in 1765, in 1820, and 1944. And clearly the river is moving back and forth across the landscape a great deal, which makes these oxbows, makes these cutoffs, makes the back swamps, but also it makes the big floodplain of this area as well. Very interesting landforms. One other type of stream deposition that's worth talking about are called alluvial fans. And alluvial fans and deltas are very similar to one another, so I've kept them together. Fans and deltas form when a creek or river reaches its base level. And when it reaches its base level, it loses all of its competence, and whatever is left in that starts to fall out of the river and starts to create landforms. If this happens in an arid environment, in a desert area, or coming out of a very large mountainous area, hitting a relatively flat valley, we get big deposits of material that create what are called alluvial fans. Deltas are created in the water or very near the water themselves. And there are a bunch of different types of deltas, including those that have perfect arc shapes, those that have little what are called bird's feet, and also rivers and streams that don't really have a delta so much as an estuary because the tide rinses material out. And then finally, there's something called a cuspate barrier island. Here are a couple of images of them. You can see here an alluvial fan in a dry, arid area. This is the Nile Delta, which is a really nice example of an arc-shaped, although there is a little cuspate formation that we have right here in the Mediterranean. If we take a look at an alluvial fan on a topographic map, we will see it look like this area in west of Furnace Creek in Death Valley, where all the little creeks coming out of the mountains to the west here carry a lot of water in the springtime and carry a lot of material. As they come, they act a little bit like braided channels. They block off their own passages, and they eventually form these really beautiful sort of arc-like shapes that are the alluvial fans. Alluvial fans can also be found in mountainous areas. Alaska has a number of smaller ones. Seward is actually built on one. Okay, last thing here. I know that this lecture is getting a little bit long, but let's just take a quick look at a couple of different types of deltas, looking at it on Google Earth. I'm going to start off with one of Alaska's best deltas, which is an arc-shaped delta, the Yukon River. And you can really see the many distributaries that come out of the Yukon producing this really beautifully shaped delta. The Mississippi River is known for having one of the world's best bird's foot deltas, very fine particles, A lot of material is unable to collect over a long period of time, and so you get this very fine delta in addition to the broader delta that is found much farther to the north from this area. A great example of an estuarian delta is the delta that's found in the Copper River, where tidal action ensures that not a lot of material collects and you have a very tidally influenced delta. And then the Kukpuk River has a pretty good example here of a cuspate delta where we have a lot of action from longshore currents producing this great form because materials carried by the river deposited in the ocean and then the ocean takes over from this point. And we can see something very similar to this in the Jago River, I think it might be called, where we have near Kaktovik these very prominent offshore bars that are created by coastal action, but are also produced by the rivers themselves. And in fact, the next thing we'll be talking about will be coastal action.